So whenever we're drawing Lewis structures, sometimes there's more than one correct Lewis structure that can be used to describe a molecule. And so these are known as resonance structures. So let's go ahead and start with a simpler example. So let's go ahead and draw a Lewis structure for ozone, for O3. Okay, so the first thing we need to do is figure out how many valence electrons we have. So each oxygen has 6, so we have a total of 18. Now this isn't going to form some form of a cyclic compound, okay? So don't even try to do that yet. We'll wait and let you guys take organic chemistry for that. So we're going to have 3 oxygens in a row. So as we look at this, we'll go ahead and start off like we did before. We'll add a single bond first. So we've used up 4 valence electrons, so that takes us down to 14. Now we need to complete the octet on the outer oxygens first, those terminal oxygens. So we used up 12 valence electrons, so we're down to 2. So we can put 2 valence electrons on that central oxygen. All right, so now both of the terminal oxygens obey the octet rule. The central oxygen does not. So let's assign some formal charges. The oxygens on the ends, the terminal oxygens, have a formal charge of -1. The central oxygen has a formal charge of +2. So whenever we're looking at things, whether or not they need to obey the octet rule or if we should minimize formal charge, things that are in the second period need to obey the octet rule. So oxygen's in that second period, so it needs to follow the octet rule. So here, if we move one lone pair in from here, the oxygen on the left, we'll end up with this Lewis structure. We'll have a double bond between the terminal oxygen and the central oxygen, and then a single bond to the terminal oxygen on the right. As we look at this, all of the oxygens obey the octet rule, but the central oxygen has a formal charge of -1, or +1, excuse me, and the terminal oxygen has a formal charge of -1. But this is a good Lewis structure to describe ozone because all of the oxygens obey the octet rule. So the other thing that you could do is instead of moving a lone pair in from the oxygen on the left, you can move a lone pair from the terminal oxygen on the right. And then you'd end up with this Lewis structure. Okay, so now all the oxygens obey the octet rule, but there's a -1 formal charge on the oxygen on the left, and a +1 formal charge on the central oxygen. So both of these Lewis structures do a good job of describing ozone. So we would say that there are 2 resonance structures, and we use double-sided arrows to denote resonance structures. Okay, so it's usually, we draw it as one or the other. Truth be told, as you go on and take more chemistry classes, we'll show resonance structures that are kind of symmetric like this, where we have a partial bond being formed between the species. But for right now, this is what I want you to be able to draw, something like that. All right, let's try another one. So draw a stable resonance structure for NO3-. So first thing you want to do is figure out how many valence electrons do I have. Okay, so nitrogen has 5, plus we have 3 oxygens, each with 6. So we have 23 electrons, plus we've gained 1 from that negative charge, so we have a total of 24 valence electrons. So as we draw our skeleton, we have something that looks like this. Now we'll add our single bonds. 2, 4, 6 valence electrons have been used up, so we have 18 remaining. And then we have 3 terminal oxygen atoms, each of which can take on 6 valence electrons. So now our skeleton is complete. As we look at this structure, all of the oxygens obey the octet rule. The nitrogen does not. Each of the oxygens have a formal charge of -1, and nitrogen has a formal charge of +2. So again, recall that things in period 2 are going to follow the octet rule over minimizing the formal charge completely. So we have a couple of options to make nitrogen obey the octet rule. The first is you can move a lone pair in from this terminal oxygen on the left. We'd have something that looks like this. Okay, so now everything obeys the octet rule. We still have those formal charges on nitrogen, +1 and then -1 here. So overall we have a -1 charge on this ion. So now the other option would be to move a lone pair from this top oxygen and then have that double bonded. So as you do more and more examples of things that have resonance structures, you're going to start to see these similarities, and you'll probably start to be able to guess how many resonance structures there are as soon as you draw the skeleton. And then finally, the last option is to move a lone pair in from that terminal oxygen on the right. And we would end up with a structure that looks like that. So there are 3 stable resonance structures for NO3-. All right, so the resonance structures we've drawn so far have been symmetric. But let's go ahead and look at an example whenever we don't have a symmetric skeletal structure. So how will you know when you're drawing a skeletal structure to not make it symmetric? So how would you know not to make this NON so it's symmetric? Well, if there's a case where it's not intuitive as to what it would be, we'll list it out for you. So we're going to go ahead and try to find 2 resonance structures, but then we have to make a decision and figure out which one is more favorable. So let's go ahead and start as we always do by figuring out the number of valence electrons. We have 2 nitrogen, so that's 10 valence electrons, plus 6 from the oxygen is 16. So as we draw out this Lewis structure, we have NNO. Add your single bonds, so that takes us down to 12 valence electrons. Now for filling up the terminal atoms, you'll fill up the most electronegative atom first. So we have 1, 2, 3, 4, 5, 6. So that takes us down to 6 valence electrons. And then with the remaining 6, you'll fill up the other terminal nitrogen. All right, so as we look at this Lewis structure, what we'll see is that the terminal atoms obey the octet rule. The central nitrogen does not. If we go through and assign formal charges, we have a -2 formal charge on this nitrogen, +3 on this nitrogen, and a -1 on this oxygen. So the first thing that I would do is this. Let's try to take care of this formal charge on the terminal nitrogen. So I'm going to move this in first. So then we're going to end up with N with a double bond, NO. Okay, so as we look at this Lewis structure, the terminal atoms still obey the octet rule, but the central atom does not. If we were to look at the formal charges, we have -1, we have +2, and then we have -1 over here. All right, so we have 2 choices from here. because we're always going to try to minimize the largest formal charges first. So as we look at this, let's go ahead and start by moving in another lone pair from our nitrogen. So whenever we do that, we'll end up with this Lewis structure. Okay, and as we look at this, we'll be able to see that now everything obeys the octet rule. We've kind of minimized the formal charge. So this is a good Lewis structure. Okay, so what's another option that we could take? Well, another option would be, instead of taking a lone pair from that terminal nitrogen, just take a lone pair from that terminal oxygen. Whenever we do that, we would have this structure. Okay, so then here are the two resonance structures. The formal charge would be -1 here and +1 here. So which of these two structures would be most favorable? All right, well, let's go ahead and start by thinking about what do they have in common. Both of these structures have the central nitrogen with a +1 formal charge. Okay, so what's different? Well, the resonance structure on the left has a -1 charge, -1 formal charge on the oxygen. And the resonance structure on the right has a -1 charge on the nitrogen. So which species, nitrogen or oxygen, will it be more favorable to have a negative charge on? So we need to go back and think about electronegativity. So which atom is more electronegative? Well, oxygen is more electronegative, so that means that this would be the more stable resonance structure. All right, so next time we'll wrap up everything and look at some common bonding motifs or common bonding patterns that we'll see, and then we'll start to move on to some molecular geometries.